So, at this point we have quickly covered everything that you already know about probability distributions. So, let us start with Mr. Bean. The first thing I am going to show you is that the joint probability can answer every question. This is obvious, but we will take a minute to show this. Our dilemma is that Mr. Bean is going to the dentist's office and he feels that he has toothache, so he might have cavity. The dentist may probe something in his teeth and then put it to test, and we say that the probe catches if that particular probe has found some microorganisms or something like that. And let us say I am able to write down this full joint distribution, right. So, there are 3 variables: toothache, catch and cavity. They are all Boolean variables. So, there are 8 possible atomic events or 8 possible states. For every state I have a value. This is my joint probability value. Okay. What is the probability that toothache is true, catch is true, cavity is true? That is 0.108. What is the probability that toothache is not true, catch is true and there is no cavity? Probability 1.144, and so on and so forth. And now suppose I ask the question, what is the probability that Mr. Bean has toothache? Right? Can you answer this question from this table? What would be the calculation if I have to ask what is the probability that Mr. Bean has toothache? What are you going to do? You are going to sum, and how many values are you going to sum? 4 values, right. Which 4 values? The left column, right, left set. So, you are going to sum all these 4 values because toothache can happen with catch cavity, catch not cavity, not catch cavity, not catch not cavity. These are exhaustive, these needs to be added for you to get probability of toothache. So, and then you can ask the question, what is the probability that Mr. Bean has toothache or cavity? And again you can compute this by this table. How many values are you going to sum? 6 values. You are going to sum 6 values, because not only are you going to sum the column which represents toothache, you are also going to sum the row that represents cavity, and some of these are common, so you are not going to add them twice, and so you will get 0.28. And last but not the least, suppose I ask you the question, what is the probability that Mr. Bean does not have cavity given that he has toothache? So, I tell you that he has toothache, I am asking that if he has toothache, what is the probability he does not have cavity? What are you going to do? Is it also going to be a sum? It is going to be a division, and in the numerator I am going to add how many numbers? 2 numbers. In the denominator I am going to add how many numbers? 4, right. So, you can see that if I want to ask the question, what is the probability that Mr. Bean does not have cavity given that he has toothache, then basically I am interested in, if you go by the definition of conditional probability, I am interested in probability of not cavity and toothache divided by probability of toothache. Probability of not cavity and toothache is this green box, because those are the 2 numbers where cavity is false, toothache is true, and the probability of toothache is the red box, because that is the set where toothache is true, and so you compute the conditional probability. So, what I have shown to you is, if I give you the full joint distribution, right, complete all the numbers have been filled, then I can add the appropriate numbers, divide the appropriate numbers to answer any kind of query. I can answer conditional probability questions, I can answer unconditional probability questions, we can answer all questions. But unfortunately, what is the problem here? What is the problem with using the joint distribution for answering queries? Exactly. How many such values do I have to maintain in my system, and how many values do I have to add and subtract? Worst case time complexity for answering a query is order d to the power n, where d is the domain size of each random variable and n is the number of random variables. Why? Because that is the number of atomic events, that is the number of states that I have, and for each state I have to maintain a value and then I have to add, subtract, and even if I might be able to do that, but even space complexity is exponential. Basically, we are just not going to be able to enumerate the full joint distribution, right. So, with this very fast analysis, we have seen that full joint distribution is amazing, extremely helpful, we can answer everything, there is no way we can maintain it. And that is going to slowly lead us towards where we want to go. But now I am going to introduce the most important concept, or first of the two most important concepts, but this concept you already know, it is the concept of independence. We are going to use this beautiful idea of independence to actually make our life simpler in reducing the values that we have to store for a given distribution. So, first of all, when are two variables called independent? Intuitively it says that look, B is called independent with A if by knowing B I do not change my probability distribution of A. I do not get any new information and that does not change my belief about A. And mathematically that means that by knowing B, so that is A given B, I do not change my distribution, that means probability of A remains the same. Okay. And of course, probability of A intersection B is equal to probability of B given A times probability of A. So, these are equivalent statements that come out. If A does not add any information about B, then B does not add any information about A. And therefore, another definition of independence is probability of A and B is equal to probability of A times probability of B, that comes from this very simple derivation. Okay. So, now why is independence important? Okay. And this slide illustrates it. Suppose A and B are independent. So, let us say in one set I have cavity, toothache and catch. In the other set I have the weather. And let us say I have sort of assumed that weather does not affect, does not add evidence to any of these three, whether you have cavity, whether you have toothache, whether you have caught the probe or not. So, now let us think about the joint probability distribution. In the joint probability distribution of toothache, catch, cavity and weather, how many original values will I have to maintain? Okay, these are simple questions, but I now need everyone to start just answering these simple questions, because I am going to explain a very important concept. So, I want everybody's concentration here. So, how many values for weather? 4. How many values for cavity? 2. How many values for catch? How many values for toothache? How many total values in my joint probability distribution? 32. Do I need all 32 to maintain the distribution? How many do I need? Because they sum to 1, I need 31. Okay? This is where we are. We actually have 31 values in my joint probability distribution. Now, let us suppose I tell you that weather is independent of all these three other things. Now, what does that mean, right? What does that mean that weather is independent of all the other things? It means that suppose I use the product rule and say toothache, catch, cavity, weather is equal to, and I use the product rule, then I can say weather times toothache, catch, cavity given weather. And because they are independent, toothache, catch, cavity given weather is going to be toothache, catch, cavity, weather does not matter. And this is called factorization. I can factorize the original joint distribution into two factors. One factor is weather and one factor is toothache, catch, cavity. Make sense? So, now how many parameters have I reduced this to? How many parameters do I need to maintain toothache, catch, cavity joint distribution? 7, because 8 minus 1. How many parameters do I need to maintain weather? 3, 4 minus 1. So, how many parameters do I need if I know this factorization to maintain the full joint distribution? 10. So, basically what have we done? We have said that by the power of independence, something that required 31 parameters now only requires 10 parameters. And this factorization could only happen because we had independence of random variables. So, therefore, it is a very powerful tool. It might be sometimes able to make an exponential distribution linear. It will be amazing. Unfortunately, you can alternatively ask the question, why are you modeling weather if you are interested in toothache? Like, why even model it? Just get rid of it. You do not need it. It is an independent variable. Keep a different set of random variables which are related to weather, and keep a different set of random variables which are related to dentist. And if you are interested in a dentistry question, use those parameters. If you are interested in weather, use those parameters. Why do you maintain them in the same system? And that is a reasonable question. There is no reason to. So, while complete independence is incredibly powerful, it is useless. It just does not happen. You do not model it. You do not model completely independent variables in your system ever. So, then we are back to square one. What do we do? And so, what I am going to say is the most important concept for today's class, and this is where we want everybody's focus, is the idea of conditional independence. Have you heard the idea of conditional independence before? How many of you are aware of it? One person? Okay. So, at least I am going to teach you something. You must be feeling like, is this an AI class or is this an 11th grade class? So, finally we are back to AI. Okay. And in order to explain this, we will again use the example of toothache catch cavity, and I am going to ask the question, what can we say about probability of catch given toothache and cavity? Okay. So, think about it. I know that the person has toothache, I know that the person has cavity, and now I am asking the question, are you going to catch the microbes? Now, intuitively, what does whether you can catch or not depend on? It depends on whether there are microbes or not in your system, and that depends on whether you have cavity or not. In fact, cavity is the cause, and then we have two symptoms or two ways to find it. One is whether you have toothache, one is whether the probe catches. Suppose I tell you the value of cavity, suppose I tell you whether let us say I tell you the person has cavity. Then do you get any additional information by also knowing that he has toothache in predicting the probability of catch? Do you understand the question? This is a very important question. This is the way you are going to ask the question. If you do not ask the question like this, you will get confused. So, by additionally knowing that the person has toothache, does my belief in catch changes if I already knew that they have cavity? And it does not, because actually catch does not depend on toothache. Now, if I did not give you the value of cavity, that is also another way of thinking about it. If I did not give you the value of cavity, I only told you that the person has toothache, would you say that that increases your probability that the microbe is going to be caught? This is an important question. You have to start thinking about it like this. So, suppose I did not give you the value of cavity. I only said, oh, the person has come in, he has toothache. Do you think that there is a higher probability that you are going to catch compared to another patient who does not have toothache? Yes. Why? Because he has toothache, he might have cavity. Because he might have cavity, my probe might catch. In other words, you should say it not like this. This is the wrong way to say it. Because he has toothache, that increases the probability that they have cavity. Because the probability of cavity has increased, therefore, the probability of catch has increased. And therefore, they are dependent. But if you already give me the value of cavity, by additionally knowing that they have toothache does not change my probability distribution, because I already know they have cavity, I already know the cause, so why bother about the other symptom. So, therefore, mathematically we can say the probability of catch given toothache comma cavity is equal to probability of catch given cavity. And similarly, we can also say probability of catch given toothache not cavity is equal to probability of catch given not cavity. When this happens, we mathematically say that catch is conditionally independent of toothache given cavity. Okay? Once I know cavity, catch and toothache are independent of each other, right? A given B is equal to A. Instead of saying that, we will say A given B comma C is equal to A given C, which basically means A and B are conditionally independent given C. Now, what I am going to show you is that when this happens, the full joint distribution does not even need 7 values, it only needs 5. And that is the most important part actually in some ways, right. So, we know that catch given toothache comma cavity is catch given cavity, catch given toothache comma not cavity is catch given not cavity. Why do we only need 5 entries in the table? Let us think about it. What is the joint probability distribution? It is probability of toothache comma catch comma cavity. Now, let us use product rule. We can use it in any way, any subset way. So, let us say we use it in this particular fashion. We say that this would be equal to probability of toothache given catch comma cavity times probability of catch comma cavity. Now, by conditional independence, what do we know? Probability of toothache given catch comma cavity is equal to probability of toothache given cavity. Moreover, we can also divide catch comma cavity into 2 steps, catch given cavity and probability of cavity. So, overall we get probability of cavity times probability of catch given cavity times probability of toothache given cavity. So far so good. Now, let us think about how many parameters do I need if I give you this factorization. How many parameters do I need to represent probability of cavity? Okay, somebody from here. How many parameters do I need to represent just probability of cavity? One. What's your name? Chinmay. Chinmay says 1. Why? Because either I can have probability of cavity or I can have probability of not cavity, but both of them sum to 1. So, we just need one parameter. Everybody with me? Now, how many parameters, and this is an important question, how many parameters do I need to represent probability of catch given cavity somewhere from the far back? How many parameters do I need to represent probability of catch given cavity? Now, what are the possibilities? One possibility is catch given cavity, one possibility is not catch given cavity, one possibility is catch given not cavity, one possibility is not catch given not cavity. Now, what sums to 1? What all things sum to 1? First, 2. These sum to 1. If I know cavity, either it is going to catch or it is going to not catch. Both of those possibilities sum to 1. And similarly, these two possibilities sum to 1. Is there any relation between the first set and the second set? No direct relation. So, therefore, to represent this first set, I need how many parameters? 1. To represent the second set, I need how many parameters? 1. So, therefore, total I need how many parameters? 2. So, for probability of catch given cavity, I need 2 parameters. Now, this kind of reasoning has to become second nature to you after the next 3-4 classes. Okay? So, try to start thinking about it in these terms. And similarly, tooth given cavity requires 2 parameters. So, therefore, what I have done is that I have used the power of conditional independence to go from 7 parameters originally to 5 parameters. We need 5 independent numbers, and we can use the power of factorization to do all your computations. Conditional independence is extremely powerful. It often is the reason how we are able to reduce the storage complexity of a joint distribution, sometimes even from exponential to linear. Conditional independence is the most basic, but also most robust form of knowledge about uncertain environments. Okay. Okay. I will take 2 or 3 more minutes and I will quickly revise Bayes' theorem for you, then we will be done with this lecture. So, everybody knows Bayes' theorem. So, this is the most important part is over, so you can go back to sleep. So, Bayes' theorem basically was developed by Mr. Bayes, right, and he said that if I get additional evidence, then how do I compute the probabilities? What is the equation? And basically he was able to say that probability of x given y can be written down as probability of y given x times probability of x divided by probability of y. This all comes from the various ways you can factorize just probability of x comma y actually, right. But now this has become the fundamental way we develop our probabilistic models. They are all based on Bayes' theorem. And there is a very famous person who got a Nobel Prize, no not Nobel Prize, but Nobel Prize of Computer Science, which is the Turing Award, for developing all this theory about probabilistic models in computer science and AI. And last time I asked you to go check it out. So, what is the answer? Yudia Pearl. Oh, you actually checked it out? All right, I am happy about it. I know you all want easy exams, so it makes sense. Now, when does Bayes' rule become important? Bayes' rule becomes important because it is easy sometimes to compute the probability distribution in one direction conditional, but difficult in the other direction. So, we are saying that x given y can be represented in terms of y given x, and typically when we have to compute cause given effect, we find it easier to compute effect given cause. Okay? Because you know when this happens then this happens, it is easy to compute probability of this. When outcome happens, what is the reason this must have happened for the outcome to happen? This is a harder reasoning for us, right, in practice. And so, we essentially say that cause given effect can be written down as effect given cause times probability of cause divided by probability of effect. But this probability of effect is not important, as I show in the next slide. But this x given y is called the posterior distribution. P of x is called the prior distribution for x, and y given x has a specific term, it is called the likelihood function. These are just terms, we just have to memorize them. So, posterior is equal to likelihood times prior divided by evidence. This is how we often write it down, right. And we will skip the example, you can check, you all know how to use Bayes' theorem to compute any value. So, you can double check this example, that is okay. But the main part I wanted to show you is that notice what is P of y in the denominator. First of all, it is all possible causes x, P of y given x times P of x, right. So, that can be written down, but moreover we do not care. Why do we not care about the denominator? Because this is going to be the same for every value of x. So, in practice what we do is that we simply compute, we can say that this is P of x given y is proportional to likelihood times prior. And so, in practice when we have to actually compute x given y, we take all possible values of x and compute likelihood times prior for them and then normalize it to sum to 1. And that is how we easily compute the Bayes probability values, right, Bayes distribution values. And we can also have conditional Bayes rule, which basically says that if I additionally give you z, all these equations hold. So, x given y comma z is equal to y given x comma z times x given z divided by y given z. So, you can put given z in everything, and that is called the conditional Bayes rule. And last but not the least, if you have to show me what depends on what, let us say I make it graphically, I say there is cavity, toothache and catch. What depends on what? Suppose there is, I say there is, cavity, there is toothache and there is catch. If I have to draw an edge from what influences what edges will you draw? Cavity to toothache and cavity to catch. You will make this kind of a diagram, a graph to represent this model. And what we are going to do starting next class is we are going to give semantics to these kinds of graphs. This is the graph, this is the Bayesian network for this particular problem. You do not know what Bayesian network is, but intuitively it says what directly influences what. Let me just add an arrow. Okay? And this particular way where there is one cause and many independent effects, this model is called the naive Bayes model. And you will learn about naive Bayes model in your machine learning course. We will talk about general Bayesian networks, but naive Bayes is one specific model that you learn in machine learning. But basically it is saying that if I know the cause, all the effects are conditionally independent of each other, because it is sometimes a naive assumption, therefore it is called the naive Bayes model. You can check that the total number of parameters here is linear in n. Why? Because you will have one parameter for cause, two parameters each for effect given cause. So, there will be total of 2n plus 1 parameters. Okay, I will stop here. We have basically covered all the basics of probability, and so in the starting next class we will start talking about Bayesian networks, the stuff that Julia Pearl got Turing Award for, and we will have 3 to 4 lectures just talking about the knowledge representation in Bayesian networks.